A current carrying loop acts as a magnetic dipole. Consider a current carrying loop. While looking from one side, if the current flows in anti-clockwise direction, it has north polarity. Then looking it from the other side, the current flows in clockwise direction and it has south polarity. Thus, current carrying loop having two equal and opposite magnetic poles separated by very small distance, so a current carrying coil behaves like a magnetic dipole. The magnetic field produced by a current carrying circular loop having radius r at a distance x along the axis of the loop is B axial equals mu 0 divided by 4 pi into 2 pi I r square divided by x cube, which equals mu 0 divided by 4 pi 2I pi r square divided by x cube. But pi r square is the area of the loop, which is capital letter A. So, B axial equals mu 0 divided by 4 pi 2IA divided by x cube. Since current carrying conductor behaves as like a magnetic dipole, this is the expression for the magnetic field at a point on the axial line of the magnetic dipole. So, we can compare this equation with the electric field at a point on the axial line of electric dipole. Now, we can see that instead of electric dipole moment P, here it is magnetic dipole moment IA. We can take it as small letter m. So, magnetic dipole moment is the product of current and area of the loop, means m equals IA. This is the magnetic dipole moment for a single turn of the current loop. For n turns, magnetic dipole moment is m equals NIA. We know the direction of electric dipole moment is from negative charge to positive charge. Negative charge is corresponding to south pole and positive charge is corresponding to north pole. So, direction of dipole moment is from south pole to north pole. Magnetic dipole moment of a revolving electron. When an electron revolves around the nucleus, it behaves as like a loop of current and it acts like a magnetic dipole. Hence, it has a magnetic dipole moment. We know m equals Ia, but I equals q divided by t. For an electron, q equals E. For one revolution, small letter t equals time period capital T. But time period is circumference by velocity. After the rearrangement, the expression of current is EV divided by 2 pi r. So, the expression of magnetic moment is EV divided by 2 pi r into pi r square, where pi r square is the area of the electron's orbit. After cancellation, the dipole moment m equals half EVR. Since V equals R omega, we can write expression as half E omega R square also. Multiply and divide with ME, then this expression becomes half E MVR divided by M. But MVR is the angular momentum of the electron, which is L. So, expression of dipole moment is M equals half EL divided by M. This is dipole moment. This is mass of the electron. This negative sign shows that the angular momentum of a revolving electron is opposite direction of dipole moment associated with it. Consider an electron is revolving in an atom with radius r and velocity v. When we are observing from the top, if the electron is revolving in anti-clockwise direction, it is equivalent to a current loop such that current flows in clockwise direction. So, when we observe from the top, since current flows in clockwise direction, the upper part acts like south pole. Then, downside current flows in anti-clockwise direction and hence it acts as north pole. Since the direction of magnetic dipole moment is from south to north pole, as per this condition, it is in the downward direction. By shifting vector r, we are making that r and v both are starting from common origin. Since angular momentum L equals r cross p, which equals r cross mv. By using right hand thumb rule, we can find the direction of angular momentum. If the curled fingers are from r to v, then the thumb gives the direction of angular momentum, which is in the upward direction. So, we can conclude that the angular momentum L and magnetic dipole moment M both are in opposite directions.